Okay, so the recording is going. So hopefully everyone's first exam went okay. That was last week. So now we're going to turn our attention onto chapters 3 and 4. With chapter 3 being on your next exam, and 4 isn't even for a couple more exams. And so just to get started, in case you weren't able to find some of the things, I'm also just going to turn my video off. If you weren't able to find the solutions to the last challenge problems, so last Wednesday's SI challenge problems, those were made into a separate solution video. Okay, and the solutions to that were posted in the typical place that all of these sessions are recorded. It was just named something different. I think I named it extra naming practice. And stuff like that. So again, right before the exams, all those challenge problems from those Wednesday night sessions will be in a separate video, but will still be uploaded Wednesday night, okay? So last Wednesday I uploaded the solutions to that. It was just a separate video and also had the naming practice, okay? And so today we have no challenge problems to get started on because, again, the last ones had to do with the last chapters. So right now I'm just going to kind of outline the Chapter 3 topics, and I'm kind of going to show you what our general schedule is for the next couple SIs. So tonight we're going to quickly go over what moles are and what molar mass is. But I believe in lecture you're covering Chapter 4 right now, so hopefully you have a pretty good understanding of that. But we're going to focus a little bit more on mass percent. That's also known as percent composition, right? So we're going to go over what that is and how to solve for it. And then a big component of tonight will be looking at empirical and molecular formulas, okay? So how to derive these from a mass percent, because that is a very typical Chapter 3 problem. We'll also, which is not listed on here, be going over isotopes and how to calculate average atomic mass. Okay, so that'll be a big topic for tonight as well. Now on Wednesday, we're going to kind of focus on the rest of Chapter 3. We're going to be looking at balancing chemical equations. We're going to be doing stoichiometry problems, so converting from reactants to products. And then we're also going to be focused on limiting reagent problems, which I know a lot of people had questions on that on the homework. And again, those problems are a big portion of exam questions. So for your next exam and the one after that, those both have to do with Chapter 3, and so we'll make sure that we go over those very heavily so that you all feel very confident with those problems. So that'll be a big chunk of Wednesday, and all of those topics will also be carried over into next Monday. Okay? Next Monday, we'll also cover just a little bit of Chapter 4, right? So we'll just start, we'll go over solubility as well as molarity and dilution, but we won't go too far ahead because the SI schedule won't follow as much your lecture schedule. We'll kind of always be a week behind. And the reason for that is the schedule for SI will more follow your exam schedule, right? So in 2 weeks from last Friday, so I guess a week from this current Friday, so about, what is that, 12 days, 11 days from now, you have another exam, and that's on chapters 1 through 3. So I'm not going to really move on too much into Chapter 4 until we're done with those, because I don't want to get too far ahead. I want to make sure everyone has enough practice and feels comfortable with the material we're currently covering for the exams. Okay? So if there are no questions up to that point, I'll kind of just leave a minute if anybody has questions, but we're just going to kind of talk about what is a mole, what is our atomic weight or atomic mass, and what is our molar mass or molecular weight, okay? So a mole is kind of like the term a dozen, right? But a mole just means 6.022 times 10 to the 23rd power of something. And that number is actually known as Avogadro's number, okay? And so the examples I have, the first one is kind of the classic chemistry example, right? A single mole of carbon is 6.022 times 10 to the 23rd carbon atoms, right? So that many atoms make up a mole. And the reason we use a mole in chemistry is because a single atom is just much too small in terms of mass, in terms of particle size for us to really study, right? We need a bigger, more something that you can visualize a little bit easier when we're working with compounds. And so this number, a mole, kind of came into existence. But it doesn't just apply to chemistry and atoms, right? You could say you have a mole of crayons if you had 6.22 times 10 to the 23rd crayons, right? Again, it just means that number of anything. But you really won't see it outside of chemistry. Now, we have atomic weight, okay? And so this is the average mass of a single atom. And these will be measured in AMU. That's typically how I'll write it. It stands for atomic mass units. But I noticed in the slides they also said that you can kind of use a U symbol to represent AMU. Personally, again, I tend to write AMU. Okay? And so how do you calculate this? You actually don't have to calculate it. Rather, you just take it straight off the periodic table. Okay? So if you're trying to get the weight of a single atom of carbon, you would look at the mass on the periodic table for carbon, and you'd see under the big C is the mass of 12.01. Okay, so when you're looking at carbon and you're talking about a singular atom, you can see based on the table that it is 12.01 AMU on average. And we'll get into what on average means in just a minute. Okay, so again, atomic weight you just take straight off the periodic table. Now when we're doing molar mass or molecular weight, we weigh this in terms of a single mole of a compound, right? So it's the average mass of a single mole of an element or compound. And this, again, is taken right from the periodic table, okay? And so when they came up with what a mole is, it's really just a larger scale version of kind of a singular atom, right? So one atom of carbon is 12.01 atomic mass units, but a mole of carbon is 12.01 grams, okay? So the numbers you see on the periodic table, the weights, are in terms of grams when you're talking about a mole of compound, okay? So a mole of oxygen, for example, when you look at the periodic table, you would find that oxygen weighs 16.00 grams per mole on average. And again, we'll get into the on average part in just a minute. Now, when you're looking at a compound, right, this is the last two bullet points on this slide. When you're looking at a compound, you have to add together the molar masses of each element. So the example I use here is just water, right? And so we have 2 times 1.008 because there are 2 hydrogen atoms, and each one of those is 1.008 in terms of weight, plus 16, which is our weight of oxygen. So if we're talking about a mole of water, we would add these together and find that 1 mole of water weighs 18.016 grams. Or if we're talking about a single molecule of water, notice that the weight is still the same, 18.016. But if we're talking about a molecule, our unit of mass will be AMU, or atomic mass units. Okay? And again, if there are any questions, feel free to stop me at any time. Okay? And so I talked on the last slide, I kept saying on average, a mole of carbon weighs 12.01 grams per mole. And the reason why it's not just a solid number and they're kind of decimal places and we say on average, it's because almost all elements have isotopes. And remember, isotopes are forms of an atom with different number of neutrons, right? So the electrons aren't affected, the protons aren't affected, it's the neutrons, which again have no charge, but do have a mass, okay? So isotopes will vary in how much they weigh, okay? And so the mass that you find on the periodic table is actually a weighted average based on the weight of each isotope. And the formula listed on this slide is how you solve for it. And we will go through some examples together, as well as a challenge problem or two addresses this as well. And so the formula is the average atomic mass, which that is the mass that is written on the periodic table. So the average atomic mass for carbon is, again, 12.01, okay, equals the mass of a single isotope, so mass of isotope 1, right, times the percent abundance of that isotope divided by 100, plus the mass of a different isotope times its percent abundance divided by 100, okay? Now, I know this might seem confusing at first. When we jump into an example, hopefully it'll make more sense. One thing I want to point out is why we divide the percent abundance, which is just listed here as percent isotope, by 100. And the reason we divide it by 100 is we just want to convert our percent abundance to a decimal form, right? So if it's 60% abundant, we're going to plug it in as 0.6, which is really just 60% divided by 100, okay? And so we will go through two examples just so this makes a little sense to you guys. The first one is a pretty straightforward question. The second one has a little bit of a twist to it. I would definitely try the last challenge problem tonight. Is a really, really good long answer question regarding isotopes. I highly recommend everybody look at it before we go over it on Wednesday's session, because I believe that question is harder than one you would see on the exam, and if you can do that, you're probably okay with these problems. Okay, so we're going to do these two. So the first one says, what is the average atomic mass of cobalt when cobalt-54 has a mass of 57.328 atomic mass units and a percent abundance of a little bit over 71%, and cobalt-62 has a mass of 62.9 AMU with about a 28.6% abundance. Okay, and so the first thing I want to point out with this problem is we have two isotopes listed. We have cobalt-54, right? The 54 just means that that's the mass number, which is our number of protons plus neutrons, and cobalt-62. Okay, and we'll come back to the second prompt before we answer that. So the solution to this is the top half of the page. And so I always start these problems by listing the information we're given at the top. So as you can see, I kind of write cobalt-54, and I wrote the associated mass that we were given from the problem and the percent abundance. Okay? Then below it, I write the same thing, but the information for cobalt-62. So again, its mass and its percent abundance. One thing that I want to point out that isn't too important for this problem, but will be very important in future problems dealing with this topic and on the exam, is that whenever you're dealing with isotopes, your percent abundances eventually have to add up to 100%, right? If in this problem we have two isotopes, right, they each have a percent abundance. We have 71.3% and about 28.6%. When you add those together, they add up to 100% of the isotopes, meaning these are the only two isotopes that cobalt has. Another thing to note, I just made up these numbers and stuff. This is not really the real isotopes or anything like that, but it is good practice. So how do we solve for this? So again, the average mass, I'll try to kind of the average mass, if you can see my cursor, if you can't, just kind of let me know. But the average mass is equal to 57.3 atomic mass units times the percent abundance in terms of a decimal, right? So we don't write 71.3%, we write 0.71385, okay? And so this is the weight of that isotope times its percent abundance plus, right, a different term, is for the second isotope. So plus, and then it's the information for isotope 2, which in this case is cobalt-62. Okay? And so the information for cobalt-62 is that it has a mass of about 62.9 atomic mass units, and its percent abundance, 28%, 28.6%, we convert to a decimal, 0.286. Okay? And what we do is we just carry this math out. So we find that the average mass, when we add and multiply all these numbers together, would come out to 58.933 atomic mass units. Okay? Just things I want to highlight. Remember, when we're multiplying, when we are taking the weight of a single isotope and its percent abundance, those you multiply, right? So we multiply 57 AMU by 0.71. But when we're looking at a different isotope, it's a plus sign that separates them, right? So in terms of this plus sign, on the left-hand side, we have information about cobalt-54, but on the right-hand side of the plus sign is all of our information about cobalt-62, okay? Any questions on that one before I go back to a slide, so we can look at the other problem? Okay, so if there are no questions, we're going to look at this next one, which is a little bit harder. This is a little bit more similar to one you'd see on an exam, so let's see how we'd approach it. So aluminum has an average atomic mass of 26.98 AMU. Okay, so because it says aluminum has an average atomic mass, that's kind of the left-hand side of my equation, right? That's not going to be involved in all the math. That's saying once we do all the math involving the isotopes, it should come out to equal 26.98 AMU. Okay, and it has two isotopes. We have aluminum 25, which has a mass of 25.8 AMU, and an abundance of 64.38%. Okay, and then we have a different isotope, aluminum 30. Okay, so we have aluminum 25 and aluminum 30. The question is, what is the abundance and mass of aluminum 30? Okay, and so again, this is just the same, but we're looking at the bottom half of this sheet. Okay, so again, I try to summarize the information. So we know aluminum as a whole, right, when we take into account all the isotopes, aluminum as a whole has a atomic mass of 26.982 atomic mass units. Okay, and now I'm just going to list the information for each isotope. So aluminum 25, again, has 25.8 as a mass, and a percent abundance of 64.387%. When we look at aluminum 30, however, we will notice that we actually don't have a weight for that isotope, nor do we have a percent abundance. Okay? And you might look down to the next step and say, what is he doing here? Remember that all of our isotopes and their percent abundances have to add up to 100%. Okay, so we have an unknown percent abundance of aluminum 30, but we know that aluminum 25 has an abundance of 64% or so, right? And we are told that these are the only two isotopes, which means that our percent abundance of aluminum 30, which I label as Z%, plus the 64% abundance of aluminum 25 has to add up to 100%. Okay, and so when we do this math, in order for that statement to be true, we find that aluminum 30 has to be in a percent abundance of 35.6%. Okay, and again, that's because the percent abundance of aluminum 25 and 30 combined has to add up to 100% abundance. Are there questions on that step before I move on? No? Okay. Give me 1 second to pull up the question. When we do problems like these, should we pay attention to sig figs? So if you can, you should always pay attention to sig figs. But what I'd say is the math in these problems can sometimes become cumbersome. And so on the exam, it's not atypical for them just to tell you in the question, give it to 4 sig figs. Okay, so in these, they often will tell you, something like the number of sig figs that they want. But if they don't, do your best to have the correct number of sig figs. I can tell you my answer for the top question has 5 sig figs, and if you did that out, that would be a correct number of sig figs. And I'm not quite sure about the bottom one if I use sig figs or not, but I can hopefully tell you at the end. Okay, so let me just keep going through. So we found that aluminum 30 has to have a percent abundance of 35.6%. So now what we're going to do is input all the known information into our general average mass equation, right? So the total average mass of aluminum we're going to have on the left side of the equation, so 26.98 AMU, is equal to our mass of aluminum 25, which is about 25.8, multiplied by its percent abundance in terms of a decimal point. So, right, 64% is about 0.64. Okay, so again, that is all the information regarding aluminum 25, and we're going to add that to the information we have about aluminum 30. So we don't know the mass of aluminum-30 yet, but we do know that it has a percent abundance of 35.6%, which again we convert to a decimal, which is 0.356. And so from here we have one unknown, x, and so we just have to go through algebraic manipulation to find the value of x, and when we solve for it, we find that x, which represents our mass of aluminum-30, is 29.046 AMU, atomic mass units. And then on the last line of this page, I just kind of summarize the answer to the question, what was the mass and percent abundance of aluminum-30? 29.046 AMU and 35.613% abundance. Okay, are there questions on this one? And again, I would say for this one, the big key to this is knowing that you can solve for the percent abundance of aluminum-30 by using the percent abundance of aluminum-25. That is kind of the essential step up to be able to solve this problem. Okay, so just a minute before I move on. And this is a type of problem that I'll try to bring up at least one problem each session before the exam, because this is something that people struggle with. But again, if you do the last challenge problem, and you can do it and you feel comfortable with it, that's about as hard as you will be able to see in one of these problems. The one that we just solved with for aluminum with is a very similar question to one you would see on the exam, including difficulty. Okay, if there are no questions on that, we're going to move on to mass percent and percent composition. And after this, I'll have people sign in. I just have a short sign-in activity, but we'll do this first. Okay, so the first thing I want to point out about mass percent that a lot of students actually overlook is that it is an intensive property, which you might remember from chapter 1. That means it's independent of mass, okay? And our mass percent as a whole is just the percent of mass an element contributes to a compound's overall mass, okay? And so if we look at the compound CO2, carbon dioxide, we would find that carbon is 27.3% of the mass in carbon dioxide. And oxygen, the other component, is 72.7% of the overall mass of carbon dioxide. Now, these percentages, because it's an intensive property, is true whether you have 5 grams of CO2, 100 grams of CO2, 10,000 grams of CO2, or even 1 mole of CO2, 2 moles of CO2. It doesn't matter whether it's grams, moles. No matter what amount you have, if you solve for the mass percent of carbon in CO2, it will always come out to 27.3%. Oxygen will always come out to 72.7%. Okay? And that is a trick that actually might help you on an exam, because a question they might often ask is, what is the mass percent of what's the mass percent of oxygen in 17 grams of water? Okay, so all they're really asking for in that question is, what is the mass percent of oxygen in water? The fact that there are 17 grams of water is completely irrelevant, because again, whether you have 17 grams or a single gram or a mole, it doesn't matter. Your mass percent should always be the same. And I think somebody asked, should we memorize this? As long as you know how to calculate that, that is fine. The only reasons I wrote the mass percent of carbon and oxygen on this slide for CO2 is just some example numbers for me to talk about when I talk about the fact that it's an intensive property. But being able to calculate this and knowing the equation is the most important part. And I'd say you'll probably pick up the equation pretty quick. Okay? Would it be given for a problem? You have to specify the question a little bit more. They might give you the percent of an element. It's probably what you'd be solving for, so it's probably the answer. Or you'll be using it for further application, which we'll get into tonight. But a straight up multiple choice question or two will probably be find the mass percent of this element in this compound. And there is an example or two later on tonight in the challenge problems. Okay, so just to go over the general format of the equation, so the mass percent, and I just have of x, and x can be any element, right, is equal to the mass of that element in a compound over the total mass of the compound. And then you multiply it by 100, but the only reason you multiply it by 100 is to turn it from a decimal into a percent, okay? And so 2 example ones that we're going to go over before we do just a very, very quick activity to sign in is what is the mass percent of oxygen and glucose? So glucose is C6H12O6. And so here we're only asking for the mass percent of oxygen. And then the second example is what is the mass percent of each element in ethane thiol? And that equation is also given. Okay. And so the first one, the glucose one, is on the left. So we're going to look at the left-hand picture first. And so I kind of take a very systematic approach to these problems each and every time. Okay? And so if they, again, we said that this is an intensive property, meaning your mass percent will it won't be affected by how much compound you have. And so I always like to assume that I have 1 mole of compound, which in this case is glucose, because I think that makes my math the easiest for me. Okay, so I'm going to assume we have 1 mole of glucose. Okay, and so you'll see in my first dimensional analysis, if I have 1 mole of glucose, I can convert that to moles of oxygen, right? So 1 mole of glucose is 6 moles of oxygen, and then 1 mole of oxygen is 16 grams, right? So this will give me how many grams of oxygen are in 1 mole of glucose. And we find that through the dimensional analysis, it's 96 grams. Now, one spot that students might get a little bit confused at is how did I know that there are 6 moles of oxygen per 1 mole of glucose? And whenever you're comparing moles of a single element to moles of a compound it's in, you use the subscripts. Okay, so this whole molecule here, C6H12O6, is 1 particle or 1 mole of glucose. Okay, and within this 1 particle or 1 mole of glucose, we can tell by the subscript of oxygen that there are 6 moles or 6 atoms of oxygen. Okay, and so again, whenever you're comparing an atom to the compound it's within, you come up with this ratio that I'm kind of circling, again, assuming you can see my pointer, from these subscripts. Okay, so again, we found we have 96 grams of oxygen and 1 mole of glucose. We do the same with hydrogen, again, using its molar mass and its ratio to glucose to find that there are 12.096 grams of hydrogen, and then we do the same for carbon, finding that there are 72 grams of carbon. Okay? So now we're going to plug this into the mass percent equation. So the mass percent of oxygen is the mass that oxygen contributes, which we found is 96 grams of oxygen, divided by the total mass of the compound. So this will be our mass of our oxygen, plus the mass of our hydrogen, plus the mass of our carbon. Okay? And then again, we multiply it by 100 to make it a percentage, and we find that the mass percent of oxygen in glucose is a little bit over 53%. Okay? And if you have questions on sig figs on this problem, I would basically just say that if you actually look at the problem that I originally wrote out, there's not a single number in it, and so you can probably write any number of sig figs for a mass percent problem if they don't give you a number. If they say 17 grams of compound, the only reason you need the number 17 is to help you determine how many sig figs your answer should have. So is it basically the molar mass of oxygen? Okay, so the question, and everyone can see it in the chat, is, so is that basically the molar mass of oxygen divided by the molar mass of glucose times 100? Yes. In this problem, it is. And the reason for that, I guess you could say every problem it's that, the reason it is that calculation is because I assumed that I have a single mole of glucose. again, if you assumed you had 17 grams of glucose, you'd get the same answer. Your numbers will just be a little more messy. But yes, if you're assuming 1 gram of compound, you calculate this by taking basically the molar mass of oxygen times its coefficient or subscript here. So, right, the molar mass of oxygen is 16. So I guess the wording there is a little off, but it would be the molar mass of oxygen times how many atoms there are. So, right, 16 times 6 is 96. Somebody asked if it was 5 moles of glucose, what would you do? Basically, instead of the number 1 mole of glucose at the very beginning, all of them would be 5, which means all of the masses would also be multiplied by 5, and when you plug it in, it would make no difference. So again, we have 5 minutes left. I apologize, guys. I have not moved this over to Zoom. That will be a goal for Wednesday's session, but if it ends, again, rejoin, and when you rejoin, that's when we'll do the activity. Okay, so the sign-in activity we'll do once we rejoin. Okay, I'm going to go through the second one, and then I'm happy to answer questions until we run out of time and just rejoin real quick. Okay, so this one, I asked you for the mass percent of each atom in ethane thiol. And ethane thiol's equation is C2H6S, with S being sulfur. And again, I wasn't given an amount, but again, this is an intrinsic property. So our mass percent does not matter on how much ethane thiol we have. Again, if they give you an amount like 17 grams or 25 grams, the only effect that will have on your answer is how many sig figs you should have at the end. Okay? And so again, for this, I assume 1 mole. So 1 mole of ethane thiol. Each mole of that has 2 moles of carbon. Each mole of carbon is 12.01 grams. And so using that process, I found that there's 24 grams of carbon. Use the same process for hydrogen to find that there's slightly over 6 grams of hydrogen, and to find that there's 32.06 grams of sulfur. When we add all of those up, we find that our total mass of ethane thiol is a little bit over 62 grams. Okay? And so again, that's our total mass or our molar mass of ethane thiol. And so what we do for the mass percent of each of these atoms is we take the amount of mass they contributed. So for carbon, that's 24.02 grams, and we divided that by the total mass, 62 grams. And again, we multiply it by 100 to turn it into a percentage. And what you'll find is ethane thiol is about 38.66% carbon, 9.73% hydrogen, and a little bit over 51% of sulfur. A good way to check these answers is to add up your percentages together and see if they add up to 100, right? Ethane thiol only has carbon, hydrogen, and sulfur, and so if we look up, add up the mass percent each of them has, they should add up to 100% of ethane thiol's mass. Okay. Are there any questions? If not, I'll probably just end this one a little quick, and then again, just enter back really quickly, and we will get right back where we left off. But before I end this, any questions?
If it said they had like 17 grams of ethaniol, would you, instead of saying 1 mole, put 17 grams?
So you absolutely could do 17 grams of ethane thiol, then convert that into moles of ethane thiol, then to moles of carbon. Basically, your dimensional analysis would just have one step kind of to the left, like your first step would be different. But if they said 17 grams, again, it's independent of how much you have mass percent. And so you could say, okay, I know that I have 17%, but for my own sake, I'm just going to say that there's 1 mole of ethane thiol, because at the end of the day, it won't affect my answer. The only caveat to doing that is, again, if they give you an amount, so 17 grams, that will affect sig figs at the end of the problem. But however many, if it's 17 grams, that's 2 sig figs. All that's going to tell you is at the end, your answer should be 2 sig figs, because there's no addition in these problems. It's just multiplication and division. And so if you want to just do the math based on 1 mole and round to 2 sig figs at the end, that will also work as well.
Thank you.
Shouldn't do the work. I always suggest you do work on an exam, at least so that when you're going back to check your answers, you can quickly do it and not have to redo the math for every problem. It also just prevents you from making mistakes, and you do have to submit your work for long answer exams. So I would suggest you write out the work. Personally, I always did it so that when I checked my answers, I didn't have to quite literally resolve every problem from scratch. I could kind of just make sure, okay, did that step make sense? Is there an obvious error I can see? Okay. Any other questions? We probably have about a minute left before this cancels out and we have to rejoin. No?